Good morning, everybody. My name is Sean Maurer. I am an engineer at the Smart Energy Design Assistance Center. Joining me today is a fellow engineer at the Smart Energy Design Assistance Center, Ryan Siegel. We're going to be covering commercial envelope and commercial lighting provisions of the 2018 IECC that we found most important or most confusing to people. Today's presentation is being recorded. We'll have the slides and presentation audio available on our website after the presentation is over. We'll also be offering certificates of completion once the course is completed. Once you receive that certificate, if you need AIA or IECC credits, email us back with your member number and we'll make sure we get that to you. Now I'm going to turn it over to Ryan and he'll take us through the first part of our presentation.
Well, thank you, Sean. So just for everyone's to be aware, towards the bottom of your screen, if you hover either towards the bottom or towards the top, a menu should appear that will include a question and answer feature that you can select. So if you do have questions as we go through, feel free to go ahead and type them in there. We will try to answer some of those as we're going through the presentation or at the conclusion. If we don't get to answer all the questions, we will plan to follow up with those afterwards. So a little bit as far as what we're looking at today, as Sean mentioned, we're going to look at 20 of the most important or more common compliance issues for the commercial envelope and commercial lighting today. We also have commercial HVAC and residential provisions that will be in the part 2 of this series coming up next week. So also looking at some of the changes from the 2015 to the 2018 and particularly focusing on the Illinois Energy Conservation Code. So a little bit about who we are. We are housed at the University of Illinois in Urbana, Champaign, and our primary mission is to reduce the energy footprint of the state of Illinois. That's both public and private sector. So our energy code training is one piece of how we do that, along with many other bits of work that we do for the University of Illinois. So today's training is being provided in part by the Office of Energy at the Illinois EPA. So we do want to thank them for their support of the Energy Code program. So as far as our technical support, we do provide technical assistance for the Illinois Energy Conservation Code, available for anyone involved with projects across the state of Illinois. So that could be building owners and occupants, design professionals, code officials, and anyone else involved with projects here in the state. So if you do have questions, we would encourage you to please go ahead and email us, energycode@sedac.org. Also have an 800 number if you need immediate assistance. So did have a question come in with regards to AIA credit. At this point, today's training, I do not have AIA credit. That may come after the fact. So everyone will receive a certificate of completion or certificate of attendance of today's presentation. So those will be emailed out after today's presentation. So even if you are not an ICC or AIA member, you will get a certificate of participation. And then at that time, if you do have an ICC or AIA number, you can go ahead and reply back to that email with the certificate. And we will record those for documentation and submission. So we do have several online resources at our website, sedac.org/energy-code. Several of those are not only archives of previous workshops and webinars that we have done. We also have several online on-demand training modules. These take approximately 1 hour to complete, and they're written at more of an introductory level for understanding. So these can be potentially beneficial resources if you do end up with building owners or building occupants saying, you know, what is this energy code? Why is it important to me? That may be a good resource for them. Something else that we do have is helpful links to other resources. We'll talk a little bit more about that in just a few minutes. So as far as which version of the code, because that's commonly an important thing to realize and understand, that there are many versions of codes. The state of Illinois has moved to the 2018 International Energy Conservation Code as the basis of the Illinois Energy Conservation Code, and that move happened July 1st of this last year in 2019. The city of Chicago moved about 1 month ahead, so theirs were for permit applications dated June 1st of 2019 or later. So one big change that we had this code cycle, from moving from the 2015 to the 2018 version, is for state-funded facilities. Prior to this, they were required to use ASHRAE 90.1. They did not have the same options that the rest of the state did. And so now with this present code cycle, state-funded facilities have the same opportunity for compliance as the rest of the state. They may choose either the International Energy Conservation Code or ASHRAE 90.1 for compliance with that. So we do like to call out some best practices when we see them, and that would be for City of Chicago has produced a compliance certificate, and this compliance certificate does allow for the design team to easily communicate to the plan reviewer as far as what the submission documents are going to include as far as compliance materials. So I had mentioned earlier with regards to some helpful links that you can get to from our website. Those displayed here on the screen are a few of those, and they include a link to the International Code Council's website for the 2018 International Energy Conservation Code, along with the state of Illinois amendments to that code for the Illinois Energy Conservation Code, and finally for the city of Chicago's amendments to the Energy Conservation Code. So rather than trying to remember all these links, go ahead and come over to the website sedac.org/energy-code, and under helpful links you can find the links to all of these for your viewing. So we do offer a series of webinars this year. We've had 4 in the past covering residential, commercial envelope, lighting, and HVAC. Coming up on May 6th, we have one covering ComCheck and ResCheck. So for those of you who may be a little less familiar or may want a refresher, go ahead and sign up for the webinar for ComCheck and ResCheck coming up for May 6th. So today we're going to cover commercial envelope as well as commercial lighting. So, and with this, I'm going to turn it over to Sean to talk about the commercial envelope.
Thank you, Ryan. First thing we're going to cover, probably the most important, is when is the energy code in force. So we're going to look at some exemptions for the energy code when you're required to meet the envelope requirements. There are some areas that have locally adopted building codes that have certain exceptions in it for facilities. Primarily, this affects agricultural facilities. But anytime a permit is pulled, that's going to trigger compliance with the Illinois Conservation Code. If you don't have to pull a permit's not paid for, then that doesn't trigger. And so those buildings would be exempt from having to meet the code envelope compliance portion. Any space that doesn't contain conditioned space, such as these unconditioned storage containers, are not required to meet provisions of the code. Buildings without comfort conditioning. In the Conservation Code and the Illinois amendments, it spells out if you have greater than 100 amps service to the building, there's going to be presumed to have some kind of electric space heating for comfort. If you can show that that service is not providing space comfort conditioning, or if you have service less than 100 amps, then those facilities would be exempt from the energy code. Last is the historic buildings. Anything listed on the National Historic Register or the Illinois Historic Register, or designated by an authorized authority as being historically significant, those facilities are also exempt from the code so that they can maintain their historical value. In the IECC itself, there is text that gives a little bit more flexibility to this, that provides provisions for sections of buildings that are historically significant. In this example, we've got the Tiffany's Dome, and that way, if you've got portions of the building that you're doing upgrades to, but a section of it is historically significant, you can preserve that section. We got a question for Chicago Public Schools. Their authority having jurisdiction is the superintendents for the state of Illinois. So they follow a slightly different code cycle. I believe they're on the 2015 IECC still. Ryan, do you remember?
Chicago Public Schools, if I recall, they have determined that they are following the 2018. They are following the City of Chicago's Energy Code, and that is just for the City of Chicago Public Schools.
Okay. Next part we're going to cover is roof assembly insulation requirements. For insulation under the roof deck inside the building envelope, where that insulation is located counts. The insulation has to be pressed up against the air barrier above and in contact with the ceiling deck. It cannot be sitting down if you've got a drop tile ceiling on the ceiling tiles. Usually when insulation is sitting on the ceiling tiles, it's there for sound dampening. But because those tiles are air permeable and so is the insulation, you're not getting the thermal performance out of that insulation unless it's pressed up against an air barrier surface. So important for insulation inside roof assembly that it's pressed up against the air barrier of the roof. For insulation above the roof deck, new to the 2018 IECC, there must be a minimum of 2 layers and the joints have to be staggered. This cuts down on air infiltration through that insulation and improves the overall effectiveness of the roof insulation if it's above deck. In the 2015 IECC, that requirement for staggering those joints was not listed. For skylight roof curbs, must have a minimum R5 insulation in that curb. There's a number of ways that can be done. You can see here they built a sandwich assembly. You could also do an internal sleeve. The only exception is if the entire roof curb skylight assembly is an NFRC 100 labeled skylight assembly, then that R5 minimum is not required because the entire assembly is counted for the skylight. Before we move on, we did get a question about cover board, if it counts as a layer. Depending on what path you're following, if you're doing prescriptive R value compliance path, you would have to meet the R value requirement. So if there's a listed R value to that cover board, you could add it to the R value of your insulating layers as well. Otherwise, you'd be using that in a U factor calculation analysis. So it could be considered as part of your roof assembly, depending on your compliance path.
I believe the question there was with regards to, does the cover board count as a layer when we say you must have at least 2 layers?
Um, I'm not sure. We'll have to dig into that question. We'll try to get back to you on that. But I would think as long as you've got 2 layers of offset joints for that roof and you're meeting your R value requirements, that would count for that offset. But most roofing, in order to meet their R value requirements, are going to have more than just 2 layers of insulation in most instances, in which case each layer is going to be staggered. So you're going to have multiple layers, and each layer is going to have the joints offset. Moving on to above grade walls and below grade wall insulation requirements. One thing we want to note here is that in the Chicago Energy Code, they delete an entire section of the IECC 402.2.2. This includes the definition for a mass wall. Mostly it's listing out the thermal capacity requirements and density requirements for a wall to be considered a mass wall, and doesn't add that back in. In essence, the Chicago Energy Code is simply stating that whatever your mass wall construction, if it meets the R value requirements in the R value tables or U factor tables, that's all they're really concerned about. But there is a little bit of an issue there in that they delete the definition for the difference between a mass wall and a framed wall. For wall insulation, it can be either all exterior, all interior, or a combination of both. Usually exterior insulation is going to be providing that continuous insulation that most wall assemblies will call for in the code now. New to the 2018 IECC for below grade walls, insulating materials used to meet the C factor or R factor tables must extend 10 foot below grade or to the level of the lowest condition floor, whichever is less. If that insulation is on the interior of the building, there is an Illinois amendment that allows that insulation to stop 10 inches above the floor. If it's on the exterior, it should be able to go all the way down to the bottom of the slab. So again, that's all the way to the lowest level of conditioned floor. So if your floor is only 8 foot below grade, you only have to go down 8 foot. But it must be a minimum of 10 foot if your floor slab is deeper than that below grade. Best practice that we see in construction is to insulate on the outside of the foundation wall and allow that to dry to the interior. This prevents any moisture in the soil from building up in that wall assembly below grade and causing degradation of that assembly. Moving on to fenestration requirements. Usually what we see, if you've got a pre-built window assembly, it's going to have one of these NFRC 400 labels tacked to it. If you've got site-built windows or factory-assembled windows, that's where compliance becomes an issue because this tag isn't stuck on that assembly when it's on site. So the code official can't necessarily walk up to your assembly and see it there when they're doing a site inspection. The way to obtain compliance for those, the NFRC has a site-built program that uses component modeling to create a NFRC 400 certificate. That gets included in the construction documents for documentation purposes. The main compliance failure for fenestration is that certificate is not provided to the code official. So it's important to have all that documentation in place and that certificate is there to provide to ensure compliance for your fenestration labeling. This is an example of what that program looks like. It's called the Component Modeling Approach Software Tool, CMAST. You can find it on the NFRC website. But this is where you're going to generate that certificate. They've got pre-built factory assembled assemblies, and they've also got the ability to pull components from multiple different manufacturers and put it into this program. Final site-built products have to be approved by an NFRC-approved calculation entity. So that's going to be an outside party that's going to check that assembly construction, They're going to probably run this model. They're also going to do a sample test in a laboratory to ensure air leakage, water leakage, and those components are met, so that when that assembly goes out to the site, they know that assembly is designed to meet compliance with the code. Moving on to floors and slab on grade insulation. Here we'll kind of cover a question that was asked about exterior insulation for slab on grade. For floor insulation, not as common in commercial construction to see wood rim joists, but certainly possible in smaller commercial construction. Very important that insulation is airtight to that rim joist to prevent condensation from getting behind. Say fibrous insulation is common. If condensation can get behind there, that's going to degrade that wood, rot it out. You're going to have long-term issues with durability of that rim joist. Another thing, floor insulation must be pressed up and maintain contact with the subfloor. If it pulls away, you're not getting the insulation value, and so you're not going to achieve compliance. Some ways to hold that insulation up against your floor deck. Commonly see wire ties pressed up between the floor joists to pinch that insulation up in place. It's probably one of the least desirable methods because it compresses the insulation. It's hard to get even insulation value out of that. You want to try to minimize compression to get maximum effectiveness out of your insulation. We would like to see the two options in the center and on the far right there, some kind of mesh or strapping that's attached to the bottom of the joist to prevent compression of the insulation. For those though, you have to ensure you've got full depth insulation to fill that cavity. That way you make sure that that insulation is pressed up against the subfloor. These are just some examples. The top left there, you can see there's some wire ties. They're actually stapled to the bottom of the joist, holding that insulation in place. Bottom center there is that mesh example. And the top right there is a spray foam application. Again, as long as that insulation is held in place and maintains contact with the subfloor, that's going to achieve your compliance requirements. For heated slabs, there's a requirement that the entire slab has R5 minimum insulation underneath. The perimeter requirement for that slab insulation increases from R10 to 24 inches below grade up to R15 to 36 inches below grade. Again, that's because you've got that additional heat in that slab that you're actually generating in that space instead of just transmitting through it for a non-heated slab. So you need a little additional insulation to ensure that that heat stays inside the building instead of leaking out into the soil around. For slab on grade construction, that perimeter slab insulation, what we're looking at here for the requirement, in the R value factor tables, that perimeter insulation needs to go 24 inches below grade, 36 for a heated slab. To answer the question for slab on grade building, does the existing insulation need to go to the footing or to 2 foot? It's that 2 foot requirement. There are a couple different ways that can be done. You can do, for the monolithic slab examples we show here, all that insulation can go to the exterior. For a floating slab on a footer, you could have that insulation wrap around the inside slab. I know we've run across some details, especially with heavy traffic, where you're having trucks or dollies rolling across that insulation that kind of creates a weak point for the edge of that slab. There are exceptions that allow structural components there that aren't necessarily insulating materials, but there are some requirements there for a thermal break, just to maximize the separation from the inside slab and the exterior of the building. For exterior slab insulation, you can use a combination of horizontal and vertical slab insulation. The total length plus depth of that horizontal and vertical insulation has to equal that 24-inch requirement, or for a heated slab, a 36-inch requirement. So you can see in the picture on the right here, for protection of that insulation, the minimum depth is 10 inches if you're going to have horizontal insulation coming out from your footer. But the total distance of depth plus length has to equal that 2-foot requirement or 3-foot requirement for heated slabs. So if you go 10 inches down, you're going to have to go 14 inches out to get your horizontal insulation to meet that insulation requirement. In many cases, we got a question here about discontinuity in thermal insulation at interfaces of roof wall and wall slab. The requirements for this insulation is that it is continuous. So if you've got some kind of discontinuity, the code would require that there be some way to either minimize that. If it's an unavoidable discontinuity, you would have to work with your authority having jurisdiction on how to comply with that. But there should be details to prevent discontinuities in your exterior insulation. So we realize there are some instances, as I listed as an example, if you've got a slab that's got heavy traffic, such as forklifts, heavy trucks, things like that. Usually what we've seen for detail there is that there's a structural component with a thermal break, but it's not actually insulation. So there is a discontinuity there, but it's to maintain the integrity of the building structure, which the code does call out for safety purposes and integrity of the building. That takes precedence over the insulation requirements. Moving on to air leakage. There are 3 components to this in the code. One of the methods to achieve thermal envelope compliance is with the pressure test of the building. That pressure testing should be done at 75 pascals, which simulates about a 25-mile-an-hour wind. And for commercial buildings, the air leakage requirement should be less than 0.4 CFM per square foot of envelope area, not square footage of the floor area. It's an important thing to note there is that is comparing the air leakage to the envelope area of the building. The other key thing to note is that 75 Pascal requirement for the pressure of the test. Though it's not as common in commercial buildings as it is in residential, we do see, especially for smaller commercials, more blower tests being done to ensure envelope air tightness. It's possible to do in larger buildings. There are truck-mounted depressurization fans, and it's also possible to do with your HVAC system. You can shut off air inlet dampers to depressurize the building, or you can shut off exhaust dampers to pressurize the building. So there are ways to do this testing properly. To do the pressure test of the building, you got to seal all intentional openings to outside the building. So doors and windows should be closed. Gravity dampers should be pinned shut so that they can't flop open. What you're wanting to test is the air tightness of the opaque envelope. So anything that's going to have a damper in or something, you want to make sure that that is sealed off for the pressure test so you can test the envelope's performance and not the tightness of the dampers and stuff, which are going to degrade that number. We particularly find this helpful for on-site fenestration, built fenestration, because it's easy to hide or miss flaws in installation of those. We see a lot of windows that break air seals over time. Thermal expansion and contraction causes sealants to come out of place. If those windows are properly installed, that shouldn't happen in most cases. So an air pressure test is a good way to see if you've got air leaks or something that's not quite installed right for those site-built fenestrations, and actually test that your installed system meets the design of that assembly. So we do like to see pressure testing of buildings, but another way to get compliance is through air barrier construction specification. So in the code specifies you have to specify a continuous air barrier for the opaque building envelope, and it should comply with materials. They have to be air barrier materials, or you have to have an assembly that's airtight. What we're looking at here is the assembly requirement. that air barrier needs to be continuous across all your assemblies. If you've got dissimilar materials joining together, you need to ensure that those aren't going to come apart, dislodge, break open over time. Penetrations, as plumbers, electricians, HVAC people put openings in the building for their run their materials through. You have to ensure that's followed up behind and those are sealed back up again. A particular note is for recessed can lightings. If those are going up into awnings or portions of the building envelope, there needs to be some kind of detail to ensure that that's not breaking through your air barrier of the building. What we show here are some examples of assemblies to ensure air barrier tightness. From the top left, the fluid applied barrier is probably the most expensive option, but it's also the most effective. It's also the least common, unfortunately, mainly due to that price point. But we are seeing that starting to gain a footing and show up more frequently on buildings. Self-adhered membranes is probably the next least common, but next most efficient. All those membranes have an adhesive on the back, and if they're properly applied and pressure rolled onto the building, you can ensure that all those joints are sealed to each other, and you're not going to have missing joints or seams that are not sealed. What we do find most common is Tyvek building wrap or insulating boards, weather-resistant boards on the outside of the building where the seams are taped. This is probably the most cost-effective option and the most common option, but it's also the least effective. It's very easy with all the seams and joints that appear in these assemblies. It's very possible that some of those will get missed. And when we find issues with buildings later on in their lifetime with air leakage issues, usually it's because a seam in one of these has been missed, or the adhesive has come away, or some kind of failure has happened in one of these joints. Just an example of something we've run across in the past. What we're looking at here is a vented patio ceiling outside the building. Surrounding this patio is supposed to be a firewall that goes all the way up to the floor above, and it's also supposed to be the air barrier for this section of the building. On the outside is a rain screen structure that's supported by an I-beam, and the floors on the inside are supported by a structural I-beam. What this created was about a 1 foot by probably about 9-inch wide gap in the building around this patio that was just left open. And what happened was they had open plenum returns on some heat pumps in this building, and those heat pumps just couldn't keep up with that load as they were drawing in straight outside air, and they were designed to condition mostly inside air. So very important if you're specifying air barrier assembly that your details call out any areas that are going to be difficult to reach, might have hidden pockets in them, and those details call out specifically how those are going to be sealed and how you're going to achieve your continuous air barrier. Another common thing we see is drywall on the inside of buildings. If you've got a drop ceiling, very often a drywall stops just above the drop ceiling. We've seen a lot in buildings and exterior walls and stuff. If you open that drop ceiling up and look at that drywall section, if you've got insulation up there in it, it's going to be filled with dirt and stuff because it's filtering air passing through that wall assembly into the space above the ceiling. So again, very important to make sure that your details explain how that air barrier is going to be continuous through the entire assembly. Moving on to the U-factor component compliance method. This is for meeting the UA trade-off if you're going to use the U-factor tables for your building. This provides a lot more flexibility to builders in how to meet the insulation requirements rather than using prescriptive R values for materials. But it is important to consider some of the potential trade-offs. For steel buildings, we've shown an example in a table here. If you're using steel framing in a building, the installed R value that you put in between those studs is going to be reduced significantly by the thermal transmission capability of that steel structure. So you see in this example thermal image, this is a building we went and visited. It was code compliant at the time, but they met code compliance without having continuous external insulation through a UA trade-off method. And you can see here that each of those steel studs, you can even see the screws going through the drywall into the studs, those really dark blue points. So really important when you're specifying, if you're doing the UA trade-off, to consider thermal bridging in your structures. Another thing to be aware of is dew point analysis for your wall assemblies. Again, having that external insulation can help ensure that if you've got air leakage from the building into your wall assembly, if you don't have that exterior insulation, it's very possible that that external layer can cool off enough to reach dew point, and you get condensation inside your wall assembly. That's going to lead to mold growth, deterioration of those materials, and other issues. Something else that we've seen in the past is ghosting, kind of the striping on drywall stuff that results from condensation developing and then dust adhering to that material and causing patches of darkness on the wall. We've provided a link here to a service that can do some dew point analysis for basic assemblies. It is a free software. It does have some limitations for the free version. There is a full commercial version as well. That's a paid program you can use to do some kind of dew point analysis. Moving on, the last component for air leakage compliance is air leakage materials. These materials have to be specified with air permeability not greater than 0.004 of a CFM per square foot of material surface area, under a pressure differential again at 75 pascals, 0.3 inches of water gauge. The IECC does list in this section, C402.5.1.2.1, what the acceptable air barrier materials are. Some things that you think might be good air barrier materials, but actually aren't: ungrouted CMUs, felt paper, brick, and probably the most important one to consider is spray insulation that isn't the proper depth. For closed cell insulation, you have to have 1.5 inches or more to qualify as that material as an air barrier. And for open cell, it has to be 4.5 inches, and we've seen some manufacturers that specify in their materials has to be greater than 5.5 inches to qualify as an air barrier. So very important when you're installing materials, especially with spray foam, that you have the proper depth to achieve an air barrier with that material. For corrugated roof decks, it's very common that we see where the roof deck sits on the wall that joint isn't properly sealed. I've seen a lot of times it's stuffed with fiberglass insulation. They do make gaskets and sealant assemblies to seal that roof deck down onto the wall assembly and minimize air leakage through that joint. For air barrier materials, again, going through the details is key. You have to specify how you're going to get a continuous air barrier with those materials. So in this example, it's showing an air blocking membrane coming down to the top of a window assembly, wraps around to a caulk sealant, and then that joins to the window assembly. The window assembly itself is rated as an air barrier. It's very important that the interfaces between differing materials have some kind of specification for how they're going to be sealed together. One of the things we like to say is if you can trace along your air barrier without having to lift the pencil up off your plan, then you know you've got a continuous air barrier. But if you ever have to pick your pencil up, you've got a break there that needs to have some kind of detail added to make sure that your air barrier is continuous and not going to have leakage points. The next thing we're going to cover is air leakage through fenestration. Again, the primary issue here is not necessarily the compliance value for the assemblies, but that this certificate isn't provided on site to the authority having jurisdiction. But again, there are, for pre-built window assemblies, this tag is stuck right on the windows. For site-built or factory-built windows, an NFRC certificate is created that has this air leakage requirement on it. And again, important to ensure that on-site assembly is accurate to the manufacturer's requirements to avoid things like this, where a gasket is popped out of place, and now this window is potentially leaking air and water into the building. Before we move on to the lighting section, we do have a couple of just comprehension questions we'd like to ask. We're going to launch a poll question here. Our first question is reviewing air barrier materials. Which is not an acceptable air barrier material? So we kind of covered a couple of examples in there. We'll see if people catch it. And the second question is, what is the primary reason fenestration products are not deemed compliant with the energy code? Is it U factor, solar heat gain, air leakage rating, or that label is missing?
While this is going on, this is also a good time to give a reminder for those who may have come in late. Following the presentation, everyone will receive a certificate of participation emailed to them. If you are needing AIA or ICC credits, you can go ahead and reply back to that email with your certificate, providing your member number, and we will go ahead and report those to AIA and ICC for you.
We also had a question about horizontal insulation for slab on grade. What's the minimum that horizontal has to extend out from the slab? That depends how deep you go. So the combination of depth of that insulation and horizontal projection outward has to equal the 2-foot depth requirement. So if you go down 10 inches, you have to extend out 14 inches. If you go down 20 inches, you have to go out 4 inches. As long as that total combination is that 2 feet, that will meet the requirements for horizontal insulation added to a perimeter slab. Give it just another few seconds here to get a few more responses in, but it looks like people are pretty set here on their answers. Okay, we're going to poll here, share the results. So our first question, I know I didn't cover in detail what the compliant materials were because they're listed in the code book, but I did specify to be careful with spray foam insulation. What I caught here, that 1.5 inches of open cell, that 1.5 has to be closed cell to be an air barrier material. All those others are specified in the code as air barrier compliant materials. So that open cell one was the correct answer there. As far as compliance for window assemblies, I specified in the couple of slides dealing with window assemblies, the main reason that they don't comply with the code is that compliance certificate isn't provided to the code official. So it looks like most people got that right, but there were a couple other answers in there. So again, just to cover those and clarify, if you're using spray foam in your buildings, be very careful that the depth of that insulation is going to meet your air barrier compliance depth. For closed cell, it's 1.5 inches or deeper. For open cell, it's 4.5 inches or deeper, or consult your manufacturer's installation guides, because we've seen some that are 5.5 inches or deeper. And for windows, make sure your code officials get those compliance certificates and window labels. I will turn it over to Ryan to cover commercial lighting.
All right, well, thank you, Sean. So we're going to start in here with occupant sensor controls. So first we want to call out that automatic shutoff is required in nearly every space. The code calls out many locations that require occupant sensing devices. For those that do not have occupant sensing devices, then time switch is generally required. Now, for this, the code does call out that you can trade, where if you have a space that requires time switch controls, you can use occupant sensing controls in lieu of that time switch controls. However, you cannot trade in the other direction. So if the code calls out that you need occupant sensing controls, you cannot omit those and use time switch controls in lieu of that. Now, it does not prevent you from using both. So if you do have a space that you do need both, or you want to use both, that's perfectly acceptable. So here we're listing the places that occupant sensor controls are required. New to the 2018 version is open plan office areas. They also made a slight tweak in the language for warehouses, specifying that that's the storage areas. Warehouse buildings typically have several different space types in them. So warehouse storage areas would have a separate requirement from the restrooms or the office areas. So with these, the code calls out a few different ways. So first, it calls out for warehouses, second, open plan offices, and third is everywhere else. So starting in the warehouse areas, uh, it requires that we reduce the lighting power by at least 50% when occupancy is not detected. And we also need to separate open plan or the open areas as depicted here towards the front of the pictures from the aisleways depicted here more towards the back of them. And also each aisleway needs to be independent of each other, which, you know, again, this is bringing logic into this, in that if someone's in one aisle picking an order, they don't need the lights on in the aisle adjacent to them because they're not in there picking items. So with that, and again with warehouses here, it's calling for a 50% reduction in lighting power at least. So moving over to open plan offices, which is the second specialty type the code calls out. And in order to meet the definition of an open plan office area, it does have to be at least 300 square feet. If it is less than 300 square feet, then that would be considered a private office. So for this, zones cannot be larger than 600 square feet. As far as your lighting fixture zones, understanding that your occupant sensing device may extend a little bit beyond that 600 square feet, but your fixture zones should be limited to 600 square feet. And these next two requirements kind of work hand in glove. First being that we have to reduce the lighting power by at least 80% when there is no occupancy detected in a single zone within 20 minutes. And then this next requirement is once there is no occupancy detected in any of the zones for the open plan office area, then the remaining 20% needs to be turned off. So these two can be done in a few different methods, one of which is you can either turn all the lights in a single zone off to meet your requirement, or the second way is if you want to have the step of 80 or 90% and then the remaining 10 or 20% turned off, then you'd need a system to interlink the different zones so that they can communicate when there is no occupants in any of the zones. Probably the easiest to install and easiest to commission would likely be the first version, where just each zone is independent and controls all the lights in that zone. The last bullet here, noting daylight responsive controls, should only activate the fixture if the occupant sensing device senses that there is occupancy. Again, this just kind of is reiterating that we don't want the daylight responsive controls to override the occupant sensing controls. It should be the other way around. That the occupant sensor controls should be the first line of sensing, and then the daylight responsive will provide the dimming only for lights that are turned on by the occupant sensing device. So we don't want an office building, here overnight, where the daylight responsive controls would say, hey, I need light, but the occupant sensing devices say there's no occupants here. We don't want those lights on overnight. So now that we've covered warehouse areas and open plan office areas, this now covers everywhere else. So if it's not the first two space types, then we get into this, which is need to be auto off within 20 minutes. That 20 minutes is a slight reduction from the previous versions, which previously allowed 30 minutes. And then the second point here is they either need to be manual on or automatic on, but if they are automatic on, they cannot bring it to more than 50% unless they fall into one of these categories in the exception. I do try to be cognizant that these are occupant sensing devices, not occupancy sensors, because typically the nomenclature used in the industry is manual on sensors will be called vacancy sensors, and auto on will be called occupancy sensors. So that's a little bit of a distinguishing nomenclature there. Now, this exception does allow for the auto on to be full 100% power for public corridors, stairways, restrooms, and private or primary building entrances and lobbies. And also noting here other areas where the manual on operation could endanger the safety or security of the room. So with this, it would be fairly difficult for a public corridor to say, okay, we're only going to bring on half the lights, and then the occupants have to do something to bring on the other 50%. That wouldn't really be conducive to good building operations. So an important feature here is this third point, is that we need to be able to incorporate a manual control so that occupants have the ability to turn the lights off in these areas. That's something that had encountered on one earlier project where it was a group meeting space with some monitors on the wall, and it was such that when the occupants wanted to display something on the monitors, it was difficult to see with the lights on, but unfortunately they had never put any controls on. So that was a frequent complaint as far as, okay, how do I turn the lights off so I can see what's on the monitor? So as far as moving over, so now that we've covered our occupant sensing areas, now moving over to, for those other areas, time switch controls. So the code notes that anywhere that you don't have occupant sensor controls, you need time switch controls. They do have a few exceptions here. And one of these that comes up in multiple locations in the code is where patient care is directly provided. So that is not necessarily anywhere that has healthcare wiring, but it has to be at the space where the patient care is being directly provided. So frequently this would be like a patient bed area in a hospital would be that. Another frequent exception is for occupant safety and security. And then time switch controls would not make logical sense for lighting intended for continuous operation. And again, this fourth point is very similar to the second one, shop and laboratory classrooms. Again, an automatic shutoff in these locations would potentially endanger occupant safety and security. So the code calls out several requirements. One of these that we note is program backup of at least 10 hours. That doesn't necessarily eliminate manual time clocks. However, there does have to be some kind of backup mechanism to keep that manual time clock running for at least 10 hours. Something else that is a little less common to see as far as when you're specifying time switch controls, but needs to be in there, is a holiday shutoff, uh, and which tells the system to go ahead and skip the schedule for the next 24 hours. And we're going to just skip a day and move on to the next day. And then the last one is an override switch that cannot override for more than 2 hours. Also, if you have time switch controls, then you have to have light reduction controls. So this provides manual controls for the occupants to reduce by at least 50%. Turning all the lights off is acceptable because that is at least 50%. So they do have some exceptions. So if you do have substantially efficient lighting, or low wattage intensity, spaces under 0.6 watts per square foot, then you don't have to have the light reduction controls in spaces with time switch controls. As far as daylight responsive controls, so now that we've gone through occupant sensing controls and time switch controls, now for daylight responsive, this is one area where I like to start with the exception first, and that is if you are able to reduce your lighting power by at least 40% of the weighted area that's in a daylit zone, then you don't have to purchase, install, and commission the daylight responsive controls. So this is why I typically like to start with this exception is it simplifies the building, which, if we can make buildings simpler to operate, they're more likely to be able to maintain that level of performance over time. So for a couple of examples, is when you say weighted area, that can be a little tricky to understand. So here in the first example, we have 50% of our area is in a daylit zone. And so we need to reduce the lighting power by at least 40% of the area, which is half. So half of 40%, I need to reduce by 20%. So in this example, if I'm able to reduce the lighting power connected down below 126,400 watts, I'm done for daylight responsive controls. In the second example, here I only have a quarter that's in the daylit zone, and so I need to reduce by a quarter of 40% or 10%. This 10% will come up again a little bit later. And so in the second example, if my connected lighting power is under 142,200, then I'm done with daylight responsive controls. So if I'm not able to get below that threshold, then I need to look at where do I need daylight controls. Need to have at least 150 watts of general lighting. This could be one or more fixtures in a space. Then if I'm over 150 watts, then I need to have daylight controls. Again, here that exceptions come back as far as healthcare facilities for where patient care is directly provided. Do have some specific applications called out for a little bit later, and then also group A2 food and drink or group M occupancies also are exempt from this. So a few of the functions that it has to have, we need to control top lit, so skylights separate from window surfaces. They do provide up to 150 watts can overlap. That's fine, understanding that you might have some areas where you do have a lot more overlap. And continuous dimming is required for offices, classrooms, laboratories, and library reading spaces. Again, because a lot of this tends to be reading applications. Step dimming can be extremely disruptive to these spaces. So another note here is the calibration mechanism must be readily accessible to building personnel, not necessarily to the occupants, and you have to be able to calibrate these from within the space. Requiring calibration to be done from a closet down the hall would not be effective, as there's no way to judge what is occurring in the space. As far as side-lit areas and what defines a side-lit zone, one thing here is the area of the fenestration must be at least 24 square feet. So if you have a fairly small opening, that would not constitute a side-lit zone because there's not enough fenestration area to allow appropriate lighting into a space. So the code book does call out several illustrations. This is taken from directly from the code book. These are also available in the online version. So we would recognize that the International Code Council has done an excellent job with their online code versions. They are highly searchable, and also they provide the illustrations directly in the even in the online version. So that can be very beneficial to use. But here noting it is the full head height of a window flopped into the room. It is not the height of the window. And then the width is the width of the window plus 2 foot on either side. As far as what that might look like on a blueprint, here this is showing it as a shaded area. This may also be shown as dotted lines or other methods to that. We will note that if you do use a shaded outline for the area, that we would recommend that there be a second print that does not show the daylight zone, so that way in the event that copies are made, you don't end up with a big black spot later down the line. Top-lit zones are called out very similarly, and they do have several different depictions of this. This is showing a skylight. They also have depictions for roof monitors and other types of top lighting areas. Question here, as far as the 150 watt exception for daylighting, is that per space? I'll touch on that probably a little bit more towards the end and verify that we give you the correct answer on that. So as far as specific applications, there are several areas here where you need specific applications, which is occupant sensor or time switch, and this is separate from the general lighting time switch controls. So you can do this either with an occupant sensing device or a time switch for these areas. And as you see here in this grocery store, the display cases would be separate from our lighting overhead. And the reason we need to keep these separate from one another is I might have cleaning crews coming through after hours, and so the cleaning crews would need the general area lighting, but not the display lighting on. So sleeping units, it also calls out for specific controls there. It does allow for key card controlled switches and receptacles to be done rather than using the occupant sensing controls. And there's also, again, this exception for patient care spaces where patient care is directly provided. So as far as You may have dwelling units in a commercial building. Commercial buildings are defined by the Illinois Energy Code is buildings that are 4 stories or more above grade, 5 or more in the city of Chicago. And so we may have dwelling units. Dwelling units may still require occupant sensing controls or light reduction controls. And there's also specific applications for non-visual applications. Again, looking at spaces and saying, do these have different times that they're likely to be needed from the general lighting. So now that we're through interior, moving on to the outside, exterior lighting, we now have 3 requirements, 2 of which are common no matter the space, and then 2 that are dependent on which type of space. There is general exterior lighting, and then the code specifies decorative lighting. Decorative lighting being for facades and landscapes. All lighting needs to have daylight shut off. All lighting needs to have time switch function, and then it's just a matter of what that time switch or setback is. So as far as what that setback is for decorative lighting, so this is building facades and landscapes, needs to turn off automatically within 1 hour of the business closing and cannot turn on more than 1 hour before the business opens. So that's for decorative, we need to turn it all the way off. If you're in general exterior lighting, we're dealing with lighting setbacks. So we need to be able to reduce the connected load by at least 30%. So that could be switched or dimming. And if it is switched, it's not uncommon where we'll see that being the lights further away from the buildings turned off and the lighting closer into the building remaining on. And it provides 3 different methods. First being the time from midnight to from midnight to 6 a.m., turning that setback on. Next being just again 1 hour of close of business to 1 hour of opening a business. So if you choose that one, then you can use the same time switch controls for your decorative lighting shutoff as you do for your lighting setbacks. So that is one option where you can overlap the functionality and combine those into a single timer. Or here it gives you the opportunity to use occupant sensing devices. Now here, and when we were inside, the limit was 20 minutes. Outside, the limit is 15 minutes. And those time switch functions have to be the same, provide the same functionality as the interior time switches. Lighting power allowances. One of the largest changes here was for track lighting. The default wattage for track lighting has been reduced from 30 watts down to 8 watts per linear foot. Now, if you do install more than 8 watts per linear foot, you do have to count the full wattage that's installed. But if you install less than 8 watts, you still have to count it as 8 watts per foot. So ASHRAE 90.1 still has 30 watts per foot in theirs, and the National Electric Code still calls out 150 watts for every 2 feet. So quite a substantial difference here. There are 2 methods here, building area method and the space by space method. The space by space method might give you a little bit additional room in the budget as compared to the building area method. However, it is much more time consuming to run that lighting calculation. So here noting, we continue to get more and more efficient lighting available on the market. And so these continue to decrease a little bit with time. The last three here, library saw the largest decrease, so it's now very similar to the office lighting allowances, which modern libraries are looking more and more like office settings. And so the next one down being dormitories. This is one of the only areas that saw an increase in the lighting allowance from 2015 to 2018. And the last one, the Performing Arts Center, is the highest value on the table. And so now even the highest value is under 1.2 watts per square foot. So we're getting down there. Showing what a difference this can make. In a library here, fairly decent size at 100,000 square feet, we have now removed, just from minimum code compliance, we can achieve much better than minimum code, but just going for the minimum code has reduced 12 tons of cooling off the system just in the lighting system. And by reducing the load on the heating and air system, that will potentially lead to smaller equipment, smaller duct runs, which can save even more money in the long run. So, as far as exterior lighting power, Zone 1 and Zone 4, nearly no projects will be dealing with. Most all projects will be in Zones 2 and Zones 3. Zone 1 is for like state and national parks. Zone 4 is major commercial in major metropolitan areas as designated by the local land use board. So for Zone 4, that probably would be things such as Michigan Avenue and State Street in downtown Chicago, and that's about it for the state of Illinois. So Zone 2 and Zone 3, this is based on, do I have residential nearby? Zone 2 is neighborhood commercial, and Zone 3 is just straight commercial. So as you can see there in the depiction, here we have mixed use, or I have commercial with nearby residential. Then I'm in Zone 2. And if you do have questions on this, go reach out to your local planning official, and they can help guide you as far as if you're in Zone 2 or Zone 3. So exterior lighting power has seen the biggest drop, in several areas being 50% or more decrease from 2015 to 2018. A lot of this is being driven by the transition from traditional high-intensity discharge sources over to LEDs. So as the lighting industry matures and gets better, we're able to achieve much better results without consuming nearly the energy that previously was required. Now that we've installed all these controls, the big thing is functional testing of all these controls. So we need to be able to test the occupant sensing controls, the time switch controls, and the daylight responsive controls. And we also have to have documentation. And so as part of this, all the documentation, which includes manuals and the reports, need to be provided to the building owner within 90 days of the receipt of a certificate of occupancy. How we have seen several jurisdictions handle this, because they don't deal with buildings much beyond the certificate of occupancy, is by requiring a letter from the owner stating they understand to be expecting these documents within 90 days. While that's not a perfect solution, that at least allows their building owner to acknowledge that they understand they should be looking for this. So as far as the occupant sensor controls, with those require is we have to test each area that of sensor combination and space geometry, and does call out the various aspects that we do have to verify. Because it is space geometry dependent, that is going to likely require the testing of most rooms that have occupant sensing devices, unless you have like a stack, because even mirror images are not necessarily the same geometry relative to the sensor in space. So a lot of that goes, there's a lot of testing involved. The time switch controls, these are a little simpler. Verifying schedules are programmed, that there is documentation of the startup schedule, because while the time switch does have to be able to maintain its program for at least 10 hours, we all understand that there are power disruptions that may extend beyond 10 hours. And so knowing what that schedule is, so the device can be reprogrammed if it loses its internal program, is very useful. And just verifying that it is properly operating and the switches, the programming is installed. Daylight responsive controls, again, here you're going through verifying the calibration and set points. And so having to go through every space and calibrating these and verifying is a lot of additional commissioning work. And again, that's why we like to call out there is that exception, so that you don't have to go through additional commissioning for this. So as far as the code, it's added a couple of new bonus measures. So if you are using the prescriptive path, which may include a COM check, that one of those, you have to choose one of the additional efficiency measures. So how are you going to take your building up to 11? And so one of these is to reduce your connected lighting power by at least 10%. So again, thinking back to that lighting daylight responsive controls exception, you can get credit here as well for that same efficiency that you've designed in. So it's a great opportunity. The other one is to add enhanced digital lighting controls, where you add additional lighting controls and control in much smaller zones, either individually addressed or no larger than zones of 4 luminaires. So we don't see these too common. However, this may be for larger buildings or buildings where you don't want to have several time switches. You may see these. Again, these are substantially more complex, which makes the commissioning substantially more difficult. So, if you don't want to go through the large control systems, there is the opportunity to go through luminaire level lighting controls. So rather than dealing with occupant sensing controls, time switch controls, daylight controls, and all of these others, one can just use luminaire level lighting controls. This luminaire level lighting controls provides embedded sensors in each fixture. So you have occupant sensing devices as well as daylight harvesting built into each fixture. So this tends to be a little bit more expensive and requires a lot more commissioning, because rather than commissioning rooms at a time, you're commissioning each individual fixture. So where we see these being more used is in office areas that might be subject to reconfiguration over time, where I may want to reconfigure spaces or change the space use, rather than having to replace the control system. a luminaire level lighting control system can be reprogrammed as the space changes. So few things that it does require is you have to be able to configure and reconfigure the systems wirelessly. Now they can use wired communication between the fixtures, but there has to be some method wirelessly to reconfigure the system. So with that, I believe we've got another couple of poll questions on our lighting here. So the first being what is required for exterior lighting controls, and the second being which systems require functional testing.
We've had a couple lighting questions come in. We got one about a home training dialysis room with a single occupant in a chair. The occupant may not move for a period of 1 hour or more because they are chair-bound and tied to a machine. So what's the code requirement for that space?
That would home I guess I'm trying to figure out if this is a dialysis. Okay, so this is a dialysis center with a single occupant. I would consult your local code official. This may be one of those cases where they would qualify this as where patient care is being directly provided for this space. So again, this was just noting, the exception is noting we don't just classify the the entire dental office or the entire hospital or the entire building as, well, it's a patient care area because healthcare wiring was used. You do need to have patient care being directly provided. So a daylight sensing commissioning question with regards to window treatments. The code does not restrict window treatments from being used. However, during the commissioning, the window treatments would need to be in their full open position to commission the system properly. Visual safety accounted for
Exterior lighting.
Yeah, for exterior lighting, visual safety, that would depend on, again, being cognizant of who you're serving and what safety needs are for the population that you're serving. Understanding that, yes, as we age, we may need a little bit more lighting intensity, but the difference between 30-foot candles and 50-foot candles, while is something that the code is typically looking at, for safety and security. That's more looking at, do I have people present and turning lights on and off? So. Question as far as, will LED lighting become part of the code down the road? The code really does not. The code tends to be technology agnostic and more specifies, here are efficiency levels, because the code doesn't want to necessarily dictate that you must use LED lighting, and then down the road a new technology comes out and all the lighting wants to change from LED to whatever the new technology is, and so it doesn't want to paint itself in the corner with that. So it just specifies performance requirements. So
Did you want to touch on the 150 watt exemption again real quick?
Yeah, the 150 watts.
Daylight sensors per space.
Yes. Here it is. The code does say spaces with total of 150 watts. So each space would be done. The 150 is evaluated on a per space method, not on a building wide method. So a space being surrounded by walls. So an open plan office area, that's one space. Each individual office is a space. So.
All right, we're going to end our polling on this question real quick. So for question 1, what is required for exterior lighting control?
All right, looks like we've picked up on, yes, we do need a timer or occupant sensing controls, and we need daylight controls. So yes, excellent. People picked up on that. And the second being which systems require functional testing. Got a fair bit here. This was a little bit more difficult because all of these require functional testing. You have to test your occupant sensing controls, your daylight harvesting controls, your time switch controls, enhanced digital lighting controls if present, and your luminaire level lighting controls. So you do have to functionally test all of these. But yeah, people picked up on this pretty good. So.
All right. We've got one final polling question on the duration of this presentation, and we're going to answer a few more Q&As that have come in while we're waiting for people to answer this poll. We got one question about whether fluid applied barriers can be applied to the roof deck, if an underlayment is required under that, or if it can be applied directly to the steel roof deck. The energy code doesn't specify one way or the other. We would have to dig into manufacturers' requirements or best practice requirements, and we'll try to get an answer back to you on that, but at the moment I'm not sure.
Yeah. The importance here is we want to make sure that that air barrier is continuous, and so making sure that whatever we use as the air barrier, that we are able to maintain that continuity from one air barrier location and type to another. So I do want to thank everyone for participating today. And so if you do have questions, feel free to reach out to us, energycode@sedac.org. Again, just want to remind everyone there is the part 2 to this session that will be next week. So feel free to register for that. And today's session will be archived on our website along with our previous ones, and we will send out certificates of participation here within the next few days.
We did get someone that wants the URLs for the component modeling software and dew point analysis. Those are, this presentation will be available afterwards. I'm going to try to pull those slides up real quick anyway. See if I can scroll back to those. So for the dew point analysis software here, that's the link right there. If you want to take a screenshot real quick, I'll leave it up for a few seconds. And then for the CMAST software, those links are there. And again, this presentation will be available for download from our website in a few days, along with full audio, so that people can have this. All right, with no further questions in our Q&A, that is the end of our presentation. I want to thank everyone for coming out and joining us. Hope you can come back for our part 2 presentation.